Hi, good afternoon, everyone. Okay, I'm truly honored to be here to share the work that I was able to participate in the last few years. And this is about teaching natural hazards to students, about middle and high school students. We achieve this through helping students understand risk and uncertainty. My name is Hee-sun Lee, and a senior research scientist at the Concord Consortium in the United States. Everything that I'm going to say would not have been possible without the wonderful team members, 4 people, members, and generous support from National Science Foundation. So today I will talk about, first, we must define natural hazards so that students can learn the way we define it. So we first worked on defining natural hazards appropriate for secondary level students, not for us, for researchers. Second, then I'm going to talk about teaching natural hazards in the science classroom. And to be able to do that, we used risk and uncertainty and how these two concepts will manifest in hazard teaching. After that, we must define activities for students to engage to learn about risk and uncertainty. So I'm going to show 3 examples of integrating risk and uncertainty concepts into the investigations of students, for students. Okay, so why we need to teach natural hazards everywhere in so many different types, everywhere in the world, in the United States, especially in South Korea, everywhere we are suffering from natural hazards. So FEMA, which is the Federal Emergency Management Agency in the United States, basically lists 18 different natural hazards, starting from avalanche, landslides, through winter weather and ice storm. Typical floods, hurricanes, typhoons here, and all kinds of threats are out there to work with us. So that means we must teach, we must learn, and we must know. Then how should we do it? So before we go in depth, let's think about natural hazards. What are natural hazards? They are naturally occurring phenomena that involve the potential for negative impacts on people, communities, and environments. And these natural hazards can trigger another set of secondary hazards and can lead to disasters. But in general public communication situations, these hazards are communicated through risk. So the risk in terms of how we see it is low risk, high risk, no risk, moderate risk. The level of risks are being communicated, as well as you are at risk of losing X and Y and Z. So that's how we started as a starting point in our team to think about how to design activities for students in the classroom. So usually natural hazards are communicated through visualizations, and FEMA listed low risk area, high risk area in the United States. By the way, I'm from United States today, so whatever I'm talking about is going to be centered around what I was able to do and find in that country. So many of things I'm going to say will generally apply to your in South Korea, in other parts of the world. So blue regions are low risk area and red regions are high risk area. Earthquakes, you know that California, I'm from California, so I have earthquake risks as well as wildfire risks, the place I live. Wildfires are usually centered on the western part of the country. And because of wildfire, by the way, 2020, August 15th, there was a lightning of 2,000 lightning that hit our area. So it created wildfire. So we were evacuated for 1 week to another area. So I'm one of those people being impacted by wildfires. And also flooding is almost everywhere near where the rivers are. And these kind of maps are constantly communicated. But when a middle school student sees this map, what the information they will be able to extract, and how they need to understand this map. That's our purpose. What kind of curriculum that we need to design and engage so that students can understand what this map contains and how I should react to these kinds of maps. So that was our foremost important goal, preparing next generation of students to encounter coming natural hazards. But these hazards are also important, generally speaking, in the United States. A framework for K-12 science education actually contains this section under Earth and space science, natural hazards. The guiding question for that is, how do natural hazards affect individuals and societies? And for middle school, they focused on analyze and interpret data on natural hazards to forecast future events and inform the development of mitigation technologies. For high school students, we focused on use of computational representation to illustrate the relationships among our systems and how those relationships can be modified because of the human activities. So these two are written. So we must address these things when we design, when we got the money from the government. So then we really think after we got money, so we must produce something. So we actually very plainly think about what students can think about. So there is a phenomenon, and then that causes natural hazards, and hazards cause negative impacts. It's a pretty straightforward thinking process for us. So phenomena are not hazards by themselves. For example, in this photo, you can see 4 different swirling clouds that indicate tropical storms in the Atlantic Ocean. Right now, not all of them, maybe all of them, not threat to the inland yet. So even though we have hurricanes or tropical storms that approach the strength of hurricanes, they are not yet hazards. So, but if it approaches to inland where people live, where critical infrastructures are there, then we must worry. That's when phenomena become hazards. And once those are becoming hazards, you know what's going to happen. Inundated streets, collapsed buildings, and lost people's lives, and everything else comes. So this one, we can communicate this one to students pretty generally. So we not just the general thinking, we have to be more specific. So we thought next, hurricane contains wind hazard, heavy precipitations, and storm surges. And heavy precipitation and storm surges can create additional hazard, flooding and landslides. Altogether, it's going to impact people, communities, properties, environments, and agriculture, everything else. So that's generally what we want to teach to students in general. So then we brainstormed. If we want to study phenomena becoming natural hazards, what kind of questions students must engage? What is the phenomenon? How does it form? How does it move, spread, progress over time? What factors make it stronger or weaker? How close is it to people, property, and resources we care? And what hazards does it trigger or accompany, secondary hazards? So these are the questions that we have been thinking. We developed activities to address these questions. Again, when natural hazards in creating negative impacts, what questions students can engage? What impacts can result from this hazard? How does the hazard cause these impacts? And what is the relationship between hazard intensity and impact severity? And who or what is most vulnerable to these impacts? And how do impacts vary across different locations or communities or even social groups? So these are the guiding questions that we had when we design investigations. Also, we want teachers to also think about. But that's not it. Well, this link, phenomena, hazards, impacts, but hazards do not necessarily cause the same kind of negative impacts, even though they are the same. So this link is mediated by likelihood as well as mitigation that we put into it. If we have a strong, relevant mitigation strategies are already in place, negative impacts would be reduced. And even though there are natural hazards coming, hurricane says coming here this way and suddenly veer to another, it happens all the time. Then the likelihood is becoming high and then zero, then negative impacts are not going to happen. So we must also address likelihood of the event as well as the kind of mitigation strategies that we can put in the face of coming natural hazard. So we had to address these two additional elements in hazard teaching. So we really put likelihood and negative impacts together. This is actually technical definition of risk in the professional community. So the risk is actually likelihood of a hazard event times negative impacts measured in dollars or casualties or loss of human things. So, and this risk is not general risk for everybody. Risk is location specific because it's natural hazard case and at a given time and for a particular type of hazard. So we actually define risk this way before we design the activity. Risk is not general, risk is specific to location, time, and people, and for a particular hazard. And we kind of wanted to address likelihood and negative impacts together as well. So, however, risk, how much you are going to lose before hurricane comes is almost impossible. So it's uncertain. Uncertain is simply that lack of certainty is uncertainty. So we cannot really estimate exactly when, where, by whom, how much you are going to lose if this one comes. So prediction in location, time, duration, damage type, extent, severity. So we don't know, simply. Also, why we don't know? Because hazard systems are complex systems, and also limitation exists when you put our forecast for everybody. Because the theories that we have about how environmental systems work, our theories are limited, scientists' theories are limited, theories that we can teach to students before this is limited. And data collection methods, data analysis methods, we do our best, but we cannot collect every piece of data out there to describe a coming hurricane, for example. And the model, computational modeling of those things, when we see this American model, European model, or some Korean model, when the storm comes, is it kind of tell you where is it going to go all the time in 100% accuracy? No, because the modeling process and the modeling algorithms are limited. They are not certain. So once these things are, then the interpretation of that output is amazingly different. Some people's interpretations to make judgments is also uncertain. Because of those, uncertainty to me is not just percentage, it's not just errors, it's not just a measurement and the accuracy of the forecasting. Uncertainty resides in the practice that creates this prediction. So when we engage students about uncertainty, it's not about uncertainty at the end. It's all about uncertainty in the process that generates uncertainty at the end. So we want to focus on uncertainty in the process rather than in addition to uncertainty in the outcome. So that's the part that we want to do. And then we also put mitigation and negative impacts together. So we also talked about what human, financial, environmental resources can be negatively impacted in a hazard event, which social groups are most vulnerable, how well communities are prepared, and what strategies can mitigate short-term and long-term impacts, and how can hazard risk and mitigation strategies be effectively communicated. So all those things are the concerns that we had before we designed the curriculum. So I'm talking about just the three investigations that embodied some of these elements. So we do use historical data for students to analyze. The top one shows yearly storm counts from 1851 to 2017. The blue lines are all types of tropical storms, and the red ones are the severe ones, of the strong hurricanes. So pretty much it's like up and down in a crazy fashion. This is the data that we are going to give to students to identify pattern over time. How much certainty students can rely on to make increase, decrease, or fluctuating. So we want students to talk about what pattern you generally see. And then we ask them how uncertain about your pattern, and then where the uncertainty is coming from on your part in making, determining the trend. And the second one, these kinds of cone of uncertainty visualizations we see all the time when the hurricane information is communicated. And cone of uncertainty visualizations is a representation of probability of where the storm might be in 6 hours, 12 hours, and 18 hours. So cone of uncertainty itself is not hurricane. Cone of uncertainty is not necessarily the path of the hurricane. Cone of uncertainty does not make hurricane bigger and bigger over time. So we give this kind of cone of uncertainty maps and have students to think about people living outside of a cone of uncertainty, whether they are going to be impacted or not impacted, and how strongly believe your decision on who to be impacted. And then the third one is actually the simulation. So we created a simulation to manipulate high pressure and low pressure systems and change the strengths of each pressure system, and then run the simulation to see where this is going, to teach students about how factors, environmental factors, or system factors determining the strength and the path of future hurricanes. So we actually put this curriculum out there, and we collected data naturally because people adopt it and they can use anytime they want. So the results I'm going to show are collected August 1st through November 15, 2023, 266 students, 7 through 13, and from 11 teachers from 8 states. And it generally kind of shows the breadth of students from early middle school through early college students. So this is a kind of type of exact task that we gave to students in the online module. So in this particular cone of uncertainty, and 93% students said yes. And then this is the simulation task. The task was the top one shows Hurricane Florence in 2018 that caused large impact, and we asked students to manipulate the simulation to create the exact path. To be able to create this path, you must actually change the locations of the pressure systems and then change the strength to make this kind of path, but they wouldn't be able to make an exact path. That's the point in simulation and modeling. modeling cannot take into account all factors, all elements of the system accurately as they occur in the real world situation. So students are supposed to fail, and the students must think about how confident they are when they create such a path and why they are certain or uncertain about the path that they created. But the goal of this system is about how pressure systems affecting the path of the hurricane. So the trend analysis one, so we showed storm counts over time and anomalies, global ocean temperature anomalies. And then we have these two put together over the same time period and make connection between the two graphs. So we have them choose the pattern and then create the certainty level, and then they talk about the reasoning. So this is the result. The certainty levels by students across 3 tasks. Risk task was cone of uncertainty. Factors task is simulation. And trend task is the data graph one. So as you can see, students do not want to say I'm uncertain. So they can, even though every task has uncertainty elements in it, but when they talk about their findings, and they really never, so there are a lot to be taught in terms of how to deal with uncertainty in the classroom. And here we can see the generally two different types. One is trend one. This is the most certain on students, and factors and risk is about similar by looking at where the somewhat certain, very certain percentages are. So I'm guessing the mathematical task, like 2 graphs and then write down patterns, does not have a real world element in it. So we are just looking at the graph and making guesses. But the simulation task, you need to create the real world hurricane as well as the risk when you have to interpret for real world people, right? For impact, not impacted. That's actually gives students a chance to be more uncertain a bit than just a mathematical exercise with the 2 graphs. So having those real-world consequences or the experience that you can bring would be an opportunity to put uncertainty and risk element more easily in the curriculum. So, and when students talked about the uncertainty, so these are the several types of uncertainty rationale that they provide in an open-ended response following their major tasks. So actually, there are 5 different types that we found. One of them, psychological uncertainty. I'm uncertain because I don't know. I'm certain because I know a lot, is the major thing. It's nothing to do with the task itself. It's all about their personal confidence, lack of experience being reflected in the certainty level. Second one is conceptual uncertainty. This one is they know science in knowledge. So they're using the knowledge to decide whether I'm certain or not certain. That is a way to talk about their confidence in the task at the end. There is an epistemological uncertainty. This one is actually epistemology has to do with the strength of the evidence to support what they found at the end. So here, students are treating their outcome of the investigation as a source of evidence and how strong that evidence is to support my claim or the task at the end. So epistemological uncertainty. And also, we also see the material uncertainty. They use the graphs as a material, simulation as a material, cone of uncertainty as a material. And students have to evaluate the material they are provided with. Is a good representation of the phenomenon that they need to think about, or how good or how bad, how easy or uneasy about manipulating those kinds of materials as a source of data or evidence. And we also see social uncertainty. What this one is that anything that we do, even among scientists, between classmates in the whole class. Agreements are not 100%. So we were thinking that's a good example of showing some social uncertainty about the same problem that they are working on with the same kind of material, we given the same kind of space in the classroom. And we indeed see some examples of social uncertainty that they were talking about. Even this social uncertainty can be me as a student doing this, me or someone else as a scientist doing this. They draw the line between scientists and me. And they actually think about scientists, what they might be doing here when I'm doing these things. Those can be brought in. Also, we know that the impact can be intensified or less intensified because people there are doing whatever they want to do. So that kind of social dimension idea can be filtered in when tasks are given to students. So these are the graphs that we saw about across 3 tasks, and students mostly focus on conceptual uncertainty for their certainty levels, followed by epistemological. And social uncertainty, most prominent when they talk about are people going to be impacted kind of task. It's obvious. But what we also found is that psychological uncertainty exists all the time. Nothing to do with the task, uncertainty in the task, everything to do with their ability, their knowledge, maybe the confidence and sadness that comes with it about the science knowledge. So that we want to work on to improve, to be more scientifically thinking about uncertainty sources. And the material uncertainty, here we actually got disheartened by looking at simulation that has the lowest uncertainty expressed. Simulation is actually all models are wrong. Somebody said simulation must bring also like a highest level of uncertainty, but they think that what they see from simulation is a less uncertainty there is like problematic. So we are trying to really work hard on how we help students. Simulation is a good tool, but it's not perfect tool. It's not the most accurate tool, and the students must know that. So the conclusion of this talk, so natural hazards matter. We all teach them. The risk concept, we putting down them to 4 for middle and high school students. And risk can be done as a whole of 4 concepts or a part of the concepts. But the curriculum as a whole can make it up to address all 4 elements. Thank you.